Hello everyone, my name is Yuhan Yao and I'm a fourth-year graduate student at Caltech. I work with the Zwicky Transient Facility to study high-energy transients. Today, I'm here to tell you about a binary system consisting of a stellar mass black hole and a low-mass star, which is the subject of two papers recently published by the Astrophysical Journal. Stellar mass black holes are born from massive stars. At the end of a star's life, the core will collapse into a stellar mass black hole, and the outer layers will be ejected into the interstellar medium. Because massive stars live fast and die young, people have estimated that roughly 10 to the 8 black holes should exist in the Milky Way. However, because black holes don't emit light, it's very hard to us to know about their existence. To our rescue, many massive stars are born in a binary system, where two stars orbit around each other and evolve together. When the massive star explodes, it leaves behind a stellar mass black hole, and the low mass star can transfer its mass onto the black hole and form an accretion disk. Accretion is a process that can efficiently convert the gravitational energy of the infalling material into radiation. So when the mass accretion rate gets stronger, sometimes these binaries produce outbursts like this one. The inner part of the accretion disk is very hot, so it shines primarily in the X-ray. The outer part of the disk and the star is much cooler, so they produce radiation in the optical. Sometimes the accretion also drives relativistic jets, which produce radio emission. So by searching for such binary systems and study them at multiple wavelengths, we can constrain parameters of the accretion disk and even the black hole itself. Historically, black hole binaries were primarily discovered in the X-ray, but because in the past few years, we have built synoptic wide-field optical sky surveys, there is nothing preventing us from finding them in the optical. AT 2019 WEY is an excellent example where the rapid rise of the outburst was first recorded by ZTF in December 2019, and the X-ray discovery came 3 months later in March 2020. You can see that the optical flux of this outburst stays relatively flat during the first 6 months of its evolution and then slightly increased. We have conducted a very comprehensive X-ray follow-up campaign of this source, which classified the X-ray evolution into 3 distinct phases, namely the stable low Hart state, the rising low Hart state, and the Hart intermediate state. We also obtained some radio observations using the VLA, and you can see that from the stable low Hart state to the Hart intermediate state, both the X-ray and the radio flux has increased by a factor of more than 10. This tells us that the activities has getting stronger in both the accretion disk and the relativistic jets. We also get some optical spectra using the Polymer and Keck Observatory. You can see that in the stable low Hart state, the hydrogen line has a very broad absorption trough and the emission core on top of that. While in the Hart intermediate state, the absorption has grown much weaker and the emission has grown much stronger. This is because that in the low Hart state, the optical emission is from intrinsic disk emission at the outer radius. But in the Hart intermediate state, the optical emission is produced by reprocessing of higher energy photons at the outer accretion disk. Such irradiation can increase the temperature of the disk surface and giving rise to the enhanced emission core. From our multi-wavelength observations, we can construct a big picture where the inner accretion disk radius has progressively moved closer to the black hole. Future observations of this system can further constrain the orbital period of the system, as well as the black hole spin and mass. With ZTF, we hope to find more of such systems in the future, so stay tuned. Thank you for watching.